Okay, so I'm coming back here. This is an equation that I wrote it before. This diagram is the same thing. That essentially sums down to here by decreasing the pressure. You are essentially bring the molecule. Actually, by compressing the pressure, you are actually bring the molecule together, and they are having an attractive interaction. But if you compress it too much, they start to have a repulsive interaction. This is essentially flip from attractive to the repulsive. And that can only happen at the phenomenological temperature called the boil temperature. And that's where you are going to see this the attractive interaction. And the compression factor can be lower than. So this is a statement. The important statement is, if this is lower than 1, and it has attractive interaction. I mean, this is a very fancy way of saying something that we can do it pretty much with a very simple instrument. Measure pressure, volume, and temperature. I can say the gas molecule at this pressure, volume, temperature condition, they have attractive interaction, repulsive interaction. So that's a pretty powerful and easier way to do. It's just a lot of experiment, I guess, to do. And this is a second one I'm going to say is a virial. And sometimes the virial expansion is what people also say. This is pretty much the same idea as a Taylor series expansion or as polynomial expansion that you do. And then they actually chop it off to get the second virial constant is the most important one. So virial itself, I think now I know, is a Latin for force. I guess when you have an interaction, they want to use this virial constant to express how the interaction is happening. And then, so let me show you how the expression come about. First one is, let me start with this. Something that I'm so comfortable with. Okay? So that's where you have no interaction. That's an ideal gas law. Then I am going to put this idea about pressure dependence. Pressure. I'm going to insert the pressure dependence. So I'm going to say this is a 1, right? And I'm going to put an extra term that is pressure times pressure squared. So I'm going to use the pressure as my sort of the handle to control what? Intermolecular distance, if you want to call it that way, right? If I bring the pressure down, bring the pressure up, and bring the molecule down. So by controlling the pressure, you can do the same thing as a volume. Just the people do that for that purpose. And then they're going to say, well, you should have a constant that we can go forever, right? So yeah.
I don't really understand what pressure dependence is.
The pressure dependence is right here, right?
No, but like.
So pressure
conceptually, the pressure is depending on something. The pressure
that's right.
depends on what.
Yeah, that's right. Pressure dependence means pressure is a handle to control molecular distance. In a way, control interaction level. Right? So this is how I can visualize something that we can measure and we can control, but by actually doing so, I mean, like I show in this syringe diagram, by compressing the gas, I'm bringing the molecule together. So I'm controlling the levels of interaction. And so what used to be not depending simple, and this is something that I can put it as an expansion to the correction. and then see how this equation can turn it out. And in the limit of this is a polynomial, and they actually wants to take those out and just keeping the first correction. This is the first correction. And the one before above it is they don't keep it in a way. So this equation becomes all of a sudden that seemingly a little bit more easier to handle. 1 plus a little deviation in a linear sense. Okay, so they just actually put this one down into this form. Okay, and then I'm going to say, instead of using the pressure, I'm going to write as E times 1 over dm. And because pressure is RT over dm, using this relationship, I am going to re-express this one in terms of this expression. So this is a one virial expansion, only keeping the second virial constant, and the B prime now just become the B, and the B is a 1. Second virial constant. So this is the second virial constant. Okay. So look at this equation, and so I'm going to write this equation down to P over dm. Can I do this? So if I divide this both equation by RT, I can get this one. I'm going to leave this one blank, and this one is 1 plus second virial constant times the. You know what this value is? We just talked about this. Yeah, that's a compression. Right? So instead of dealing with the compression factor, we are talking about compression factor dependence on the essentially 1 over molecular volume. So I use a pressure. That's how the textbook dealing with. But I can just start from here. Do you know what this means? Molar volume over. If I do that, that is what? All right. That's this is volume divided by number of moles, and so that's what it is. So what does this means? N over V. You see, this will come up once again in the van der Waals equation. That's a number of moles per gas in volume V. So if you're talking about two different 1 over Vm, one has this, the other one has only this, but this one has that. It represents density. What I call the probability for you to find this gas molecule. So this is a one that it is a term that is the density term, and how depending on the B value, your B can, when B is positive, repulsive interaction, when B is a negative, is an attractive interaction, and we can expect that. Okay, so here's actual data. This is the one that people can tabulate that, and for argon, B is minus 21.7. I'm going to leave the unit as a blank, because I want you to get used to dealing with this unit. So let's say at 273 Kelvin at 600 Kelvin. There are two temperatures. Okay, one is this value. The other one is the other value. So I want you to figure that out. Which one is which temperature? So, what are the chances for me to have a more attractive interaction? Lower temperature or higher temperature? Lower temperature, right? That's the concept I talked about. Temperature has to be lower than boil temperature to actually you can have attractive interaction. So this one has an attractive interaction, right? That's from our experience. So we know this one is definitely a real repulsive interaction, right? They repel each other. And so which one represents the repulsion case and attractive case? This one? Your negative value? That's an attractive, right? So this one is 273. This one is 612, right? High temperature. They all have a repulsive interaction. And let's talk about the unit now. So what's the unit of Z? Actually, I did not talk about the unit of Z. The compression factor, what's the unit? Is it pressure, volume, pressure times volume divided by RT? What's the unit? Anyone? Pressure times more, yes. That's right. That's where I'm getting, right? So in a way, if you guys do not know the answer, typically the PChem answer either 0 or 1 or unitless. Those are one of the usual suspects. This one is no unit. And then it's actually, like she said, that's a better term we call unitless. So your final term has a unitless. So this term should have no unit, right? So what's the unit on this?
Number of moles of oil.
That's right, mole per liter, for example, right? So what's the value on this? Inverse of that unit, right? Volume per mole. So what I wrote down in here, they provide me the value of, I mean, each area people using different one. So this is a one that in a way, the PChem is a little bit about dealing with, when you're dealing with an equation, have an extra time to think about what does it mean, and the unit of each constant that I'm dealing with, and you have a one step closer to get this one done, okay? And then plugging the equation down. Okay. Okay, so this is a second virial constant that I just talked about.